seems like the joining of the meeting stabilized. So let's continue. Okay, so this presentation, this webinar, is intended specifically for beginners who are using PLCs in their plants to perform basic control systems, but they need some additional information on how the PID works and what's the principles it operates on. So the keyword here, this is part 1. So this will be the basic introduction. So part 2, we will look at more in-depth mathematics and also interfacing between other devices like GOTs, SCADAs, VFDs, and so on. And then part 3 will be more advanced. So yeah, this is part 1. So there will be a lot of theory involved here. So we just go to the agenda. Yeah, so there will be introduction. We can cover some basic theory regarding PID. We're going to look at the advantages of PID, the purpose of it, the process flow from a PLC perspective. So this will be a generic flow, not specifically to the Mitsubishi PLCs. That's any controller, just a generic flow on how the data is being handled. We're going to look at a couple of definitions and term descriptions. Okay, so these two will be tedious points because there's a lot of definitions and terms to be discussed. However, this will be needed for your PID for two things: for the configuration of your PID, and also for the tuning and fine tuning. In many cases, you will also use the auto tuning, which we will do in part 2. So yeah, those definitions needs to be understood each term. Then we're going to look at the algorithm factors. That would be the P and I and D factors, which we're going to look at. The controller structure, how the controller receives the data and process it and provide outputs. The basic process block diagram we can have a look at. The operation we can discuss. And then there will also be a small practical at the end where I will just demonstrate on how to configure a simple PID block using GXWorks3. So this will be like a practical demonstration. And then we'll also look at the abbreviations and acronyms at the end. Okay, so let's start here. Right, so as I mentioned, we'll only look at the basic / introductory elements in this webinar for PIDs. Okay, so one of the bigger problems we see with PID control, especially when it comes to supporting clients, is there's a gap between the theoretical part and the practical implementation. And that gap is not easily bridged. Okay, so, it's mostly bridged by trial and error and testing and simulations. But we will try to facilitate that process to make it faster and more effective and more efficient. Okay, so PIDs, it's very popular in both process instrumentation and control, as well as factory automation applications. Okay, and it's also the most common control algorithm used in industry. So it is actually accepted as the industrial standard for continuous control in both those fields. So the function of a PID is to provide a simple and effective automatic control philosophy. Okay, so it provides a effective control-based solution which eliminates oscillation. And by eliminating oscillation, you optimize your process and your system efficiency, and also increase the productivity of your system and also the lifetime expectancy of your equipment. If you think about your actuators like your valves or your motors, you don't want the valve or motor to oscillate around a set point to try and maintain a set point based on the process variable. Because then obviously with the ramp up of the motor will get hot, and also the valve, the wear and tear on that. So a PID effectively eliminates all the unnecessary oscillations. That is what a PID is for, especially a PID which is correctly fine-tuned for the process. Okay. So control systems are everywhere. You'll find it in every plant. You get different kinds of control systems. We'll have a look at that in a moment. So basically, for a control system, you have an actuator, which is controlled by your MB, which is your manipulated value. Okay. And you'll also have a sensor for your process. The sensor can be a transmitter or transducer for, say, flow rates for fluid, and also system pressure, can be temperature, can be speed, in some cases like in VFDs. It can also be level. That's also very popular. So anything that you measure with an analog signal, that can be a process variable. Okay. Anything that you need to display as an engineering value on the HMI, that would be a process variable. Okay. So PID provides the PLC the ability to make decisions. So decision-making capabilities, very basic. We're not talking about AI or something like that, just basic decision-making. So it's a bit above the standard logic, the arithmetic logic and comparative logic. There's more algorithms involved to make these decisions. So that's where PID comes in, okay? And obviously, as of all algorithms, it is based on mathematical equations. Something we won't cover in depth in this introductory course, but we will just look at the variables that's involved, just so that, everybody has an understanding. So the mathematics for a PID system, it's built around error detection. So your error is basically your process variable, the difference between your process variable and your set point. So a PID control system wants to force that error to 0. So that's what the mathematics will be based upon. Okay, and also how to do that most effectively and efficiently in terms of time. Okay, so there is a popular misconception that you will need to have advanced mathematical knowledge for such algorithms. No, that's not correct. Just need to know the basic rules and what every input and output means, and then you can fine-tune the PID pretty well. Also, as mentioned, for our FX5s, our IQRs, and for other products, you can do fine-tuning, auto-tuning to find your efficient gains. So we'll look at that. So PID is the successor of continuous control philosophies, okay? And it's very simple. So that's one of the advantages of PID. It's a simple, relatively to other control philosophies, a simple algorithm to apply. And another reason why it's so popular is because it's very robust and reliable. Okay, so it's consistent, robust, and reliable. So that's why it's used a lot in the plants. By robustness, I mean that it adapts. So if you control tank level, for instance, the control process will take into account not only the consumption of the fluid in the tank level, for instance, but other factors as well. So, for instance, if the tank expands due to temperature, and then obviously the volume changes, or if there's leaks in the pipes and tanks and so on. All of that factors are already taken into account in your PID control system when you fine-tune it. Okay. So the PID, remember, it's always try to get a 0 error, irrespective of how many leaks you have in your tank and your pipes, or how the tank changes, tank sizes change, and so on. Okay. So in simpler terms, if you have to explain what PID means, it's a self-adapting process variable regulator. So process variable, that would be, like I said, temperature, pressure, level, so on. Self-adapting means it's auto-correcting it, the error. And yeah, so it does that regulation constantly and continuously. So PID control, that is a control loop, continuous control system. So control loop means it must have feedback. So the feedback in this case would be equal to your process variable. Okay, so it would be a sample of your process variable. So feedback is normally derived or denoted as FB, process variable as PD. So feedback and process variable, essentially the same thing. Okay. From there, it calculates the error deviation based on your set point. And it does that in a constant, continuous fashion. Okay, so it's real time. So it's as fast as the scan cycle or a PID cycle allows it. Right. So control systems divided in two main groups: digital discrete control systems and analog continuous control systems. So the former is a more primitive control system, and in some cases it is the preferred control system. It depends on your hardware, okay, that you have. So it's based on digital discrete feedback and outputs and inputs. So it's on-off signals. And in some cases, you won't see a feedback for a digital control system. So then you will rely on sequential control. In other words, timers and counters and so on. So it will be a predefined control system. Okay, so it's used in basic control systems where efficiency is not that big of an issue, as long as the tank levels are maintained or the temperature is maintained as required. So, and as mentioned, it will also be dependent on your hardware. Okay, so the acronym for PID is proportional integral derivative. So those are three terms that's used for the PID control system. That's why in some cases, in some literature, in some plants, they call it a three-term controller, not a PID controller, because there are three terms. So they call it a three-term controller in some cases. So just each one of these components plays a role. You can have a look at that in depth in a moment. And they can be used independently, separately for a control system, or they can be used in conjunction, combined with each other for your specific control philosophy. So by that, I mean, you don't have to have a PID controller. You can also have a PI controller or a P controller or a PD controller. But you always have a proportional part. So the latter control system, which is the continuous control system, it will control the process via an algorithm. Okay. And the most common of these, as mentioned, will be a PID control system. It's worth mentioning that continuous control systems can be open loop, okay, without feedback, okay, but that will not be a PID control system. PID needs a control feedback or feedback. Okay. So a rough estimation would be based on if you look at all the audits that was done worldwide by third-party researchers, 95% of all closed-loop systems in the industry are PID control. So it's quite important to understand this control system for implementation and optimization for your system. Okay. As mentioned, the distinction between these control philosophies will be hardware dependent, mostly, in most cases. For instance, a PID output is mostly analog. So in most cases, it will require a control valve. So there are exceptional cases where a shuttle valve is used in conjunction with a PID, where it's converted into discrete control. But standard and normal conditions, it will require analog signals, continuous analog. So this will be for both inputs and outputs. That's the most popular layout. Okay. However, as mentioned, there are cases where discrete inputs and outputs are used for PID, but that's extremely rare. That's not the standard. Okay. For that, you'll use discrete control systems. Okay. So a VFD, so VFD that works on analog signals, continuous. So VFD can be connected to a process variable of the plant, and its feedback will be controlled by PLC's algorithm, and then the VFD in turn will be controlled by your MV to control the speed of the motor, which would in turn control the speed of the pump or fan or blower or whatever process you have, to try and reduce the error to zero. Okay. So just to summarize, all PID control systems are continuous control systems, but not all continuous control systems are PID control systems, okay, as opposed to discrete control systems. So two main categories will be your continuous control and discrete control, and then of both sides, you get different types of continuous control or discrete control. But the one that we'll look at today will be the PID control. Okay. So the reason for this classification is you need to understand what type of control system you're going to implement on your PLC, depending on the hardware that's available in the plant, or the hardware that's standardized in your process or your system, or the hardware that's allowable for your system. So if the plant for a certain process requires shutter valves, or the standard like that, or the budget demands that, then obviously it will you will have to adapt your control system for that shut-off, which will, in most cases, be a discrete control system. Okay. So therefore, PID is not a universal solution for all control systems. That's what the purpose of this classification is. But it is a universal solution for most continuous control systems. Right. A couple of advantages of PID control systems. So first of all, it can be used in almost any plant process. Any plant process where there's a continuous adaptation to be implemented to achieve a certain value, you can use a PID. So like I said, you can use it from furnace temperatures right through to tank level controls, or to system pressure for fluids. Anything with PV that needs to be regulable can be used by control system, PID control system. Okay, it's also relatively simple to understand and easy to apply. Okay, with all the PLCs, you would need to understand the fine-tuning methods to get the optimized PID. However, with new equipment coming out, like our IQ series of PLCs, with the GXWorks 3, and so on, it does have a auto-tuning function, which you can use to optimize your PID, which we'll be looking at in part 2 of this webinar series. Okay, so it also provides a scenario where your technician or engineer or designer can have a set and forget implementation. So you don't have to go every day and fine-tune your PID. And it's self-sustainable. The PID is self-adaptable, self-sustainable, and therefore minimum maintenance. Okay, and it will retain a relatively well-regulated system if you compare it apples for apples with other control systems in terms of maintenance. Okay. Okay. So PID system is a universal control system, as it can be used for both small and fast-acting processes like motion control, as well as larger and slower processes like for tanks and temperature and so on. Now, I have to point out it's a universal control for the sizes and equipment in the plant, but it's not a universal control system for discrete control systems. Okay, so just to have to point that out. Then another advantage of PID control system is as mentioned, many of the implementations and the software applications allows you to auto-configure it and tune the PID depending on your requirements. Okay, to optimize it. So purpose of PID is to manipulate the output variables that a controller receives, so that the controller can maintain a zero error in the process. So like I said, the error is the difference between what you want, the set point, and what is actually happening in the plant, which is the process variable. Okay. There are two required measurable outcomes of a control system with a PID. You need a stable control system. So like I said, you don't want something that oscillates. And this stability will be determined by the MB, which is your output of your controller. And also it needs to have a relatively fast response to the errors that it has. Okay. However, these two requirements are contradicting each other. Okay. You have to fine-tune a PLC to take both of these into account and get a balance. Okay. Right, so just a generic flow of the process flow of PLC. So the first step will be the initiation of your PID controller. So that's where you sample your set point, which you get from your user, which can be from an HMI or from SCADA. It can be hard-coded into a PLC as a constant. There are various ways to adapt that. You can even have that as an analog input for user definable. Okay. Then it would calculate the error. So like I said, the error would be what's actually happening in the field, your set point and the process variable and your set point. And then it would, based on that error, it will calculate the P factor. So the P factor is your proportional factor. And the elements that plays a role in your proportional factor is your gain, your P gain, okay, which we'll have a look at later. And then it would look at your totalizer value, which is your I value, your I factor, your I gain. So it will calculate the totalizer factor. And then we'll also look at your D factor. So once again, it would calculate that based on your gain. Traditionally, for most systems that doesn't need fast response, the D gain is either negligibly small, so like relative to a PNIB that's omitted, small, or it's not used at all. So you just use a PI controller. Okay. However, there are a large quantity of systems that use a D as well, because the D has a prediction factor due to the rate of change. So sometimes it is included. Okay, so then we'll update the error, okay, with the current error. So now your current error becomes the past error, and your past error is removed from the system. The PID will perform its calculations, and then the MB, the manipulated value, will be sent to your actuator. From there, the process continues. Okay. Just some definitions, because we did mention the term closed loop. So closed loop, in short, is any system with a feedback. Okay, and that feedback will be a reference control. Okay, so it will be used as a reference of what's currently happening in your process. Am I achieving success, or do I still need to make changes to my gains, to my P factors, I factors, and so on, so they can reduce the error. Okay. So the key point of a PID control is to minimize the effects and the disturbances of the PD, the process variable. So you have to minimize that, because you don't want a plant that oscillates. So oscillation, I mean your process variable swings around your set point, above, below, above, below. You want to avoid that. You want to get a steady state output. Okay, set point. So set point is what you want, the desired process variable. So that's user defined usually. And it's mathematically depicted as R as a function of T. And then your process variable. So that is what's actually happening. Okay, that's not your desired outcome. That's what's actually happening in your process. That's being measured by your sensors and being sent to your PLC. Okay. So the plant is the system we want to control. So we're not talking about a production plant or a process plant or a batch plant. In this case, a plant can be anything you want to control. It can be a tank, can be conveyors, can be a furnace, anything that you need to control. Okay, so anything where the process variable is being measured and anything where the set point is being determined. So that would be your plant. Okay. A plant can be a combination of sub-plants, where there's a combination of different process variables and set points. And then you move into the area of cascade control. Okay, so that's a bit of more advanced control system, which we'll look at in future webinars. But for now, we'll just look at a single PID control system, no cascade control. Okay, your actuating value, as mentioned, that is your analog signal, in some cases, digital signal, this digital discrete, but for the theme of this webinar, that will be your analog control signal that goes to your actuator to control your actuator, which in turn controls your plant, which in turn affects your process variable, and which will affect your feedback that goes back to your PLC. Okay. Controlled variable. So in some hardware, some manuals, some books, you'll find the term controlled variable. Okay. So control variable, what they actually mean is it's a process variable for the plant. Okay. So as I mentioned, there is a gap between the theory and practical implementation. The theory, I mean purely the textbooks of the calculations. They don't refer to process variable anywhere, many of them. So control variable is your process variable. So that's just something to take into account. If you are confused what that is, because there's also your PLC resolution output and so on to take into account, that needs to be scaled. If you're confused, it's anything that has a SI unit, like kPa for pressure and cubic meters per hour, and anything which has a SI unit, that would be a process variable in this case. Okay, lag time. So lag time is a time constant. Okay, so like I said, this is for if you want to do manual fine-tuning of your PID control. So they've used a lot of methods for fine-tuning, like the Ziegler-Nichols method and so on. In this case, they use a lag time as a variable for this fine-tuning. So the lag time is the period from when the PV, which is process variable, starts to change, adapt, from the point where it reaches 63.2 of your set point value. Okay, so that is to determine the lag of your control system, the delays, and how to correct that. So that would be the variable that would be used there. Okay, then you get your dead time. So your dead time is the time that your controller output affects your process variable. So when your controller sends an analog signal update to your actuator, the moment it's sent to your actuator, from that time to where your process variable actually starts to change, that's called a dead time, DT. So it's a function of time. Okay. Then your error. So your error is, like I mentioned, that's the difference between your process variable and set point. I just want to point out that the error can be both negative and positive, depending if you have a direct or forward control system or a reverse control system. The error can be negative or positive. So in other words, if you have, for instance, a forward control system, your error will be your set point minus your process variable. Whereas you have a negative control system, it can be the set point minus the process variable. So those two can be swapped around depending on the control system. Okay. Manipulated value, as mentioned, that is the output of your PLC that goes to the controller, usually an analog signal. And so for those who use these type of signals, that would be traditionally milliamps for long distance applications, or voltages, 0 to 10 voltages for short distance applications. And yeah, it will never be temperature, because temperature, that will be a process variable. So it will be a signal, analog signal, voltage or current analog signal. And that is depicted as YT. In some cases, in some control systems, that is depicted as UT. So just take that into account so you don't get confused. Then your steady state error. Okay, so steady state error is an error that you'll get if your I, your integral factor, is too small. So what happens is your PID control system will control your output of your process variable, the output of the process variable value, okay, via the set point, until it stabilizes right below and sometimes above the set point, and it doesn't reach the set point ever, because the changes are too small to reach the set point. So it will take a very long time. So it looks like a straight line. They're very close, but they never reach that. So that would be your steady state error. So one way to fix that type of error would be to increase your I gains. Okay. So just another note, because we spoke about two different errors here. We spoke about the error E and then your steady state error. So the error E is your instantaneous error, what's happening currently. That would be your difference between your process variable and your set point, and must always be 0. And then your SSE, which is steady state error, that is the error that you will get when your controller doesn't control anymore. It reaches its stabilized output, and there will be a small percentage error, the difference between set point and process variable. So that is an error over time. So that would be fixed by your I gain, because your I gain looks at a historical time. Okay, so we spoke about gain a couple of times. So each one of these coefficients, the PID coefficient, has to have a gain, which is either user-defined via fine-tuning or PLC-defined, which is done via auto-tuning. Okay, so these are static variables. Once they are determined, they are used as constants in the PLC. Okay, so they can be seen as amplifiers for each of those coefficients. So the larger the value is, which you multiply with, the larger effect each one of those coefficients will have. Okay. So I just want to point out that just roughly your P is your proportional control. So it will look at your current instantaneous errors. With the I, that would be your integral control. So that looks at historical time. That's why it's popular to be used for control of your steady state errors. And D, which is the least popular of the three coefficients, but there are many systems that use it. It looks at the rate of change. So it looks at the future. It will predict what the error will be and proactively try to manipulate the output in B to address that predicted error. Okay. So those are the three gains that you use for PID. Yeah. Output. So as mentioned, that's your output of your controller. It's depicted as YT sometimes or UT, depending on the diagram that you use. Sometimes in some diagrams you use both of them. And in that case, your YT will be the feedback value comes out. Okay. So that's just something to take into account. But like I said, that's your analog signals. That goes up with that's your PLC outputs. Right, then the cycle time. Okay, and some manuals they call it the cycle period. Okay, it's a time that it takes for the controller to perform the PID algorithm calculation each time. So the rate it does that. Okay, so this is configurable in our PLCs. You can change that. The faster it is, the higher the performance, okay, of the output. But it's also very resource intensive on your PLC from both a software point of view, the CPU, as well as the hardware, the analog parts. So that must be taken into account. So the frequency, the higher the frequency, the higher the performance. And the frequency is indirectly proportional to your cycle time. So the larger your cycle time, the lower your computation frequency, the lower the performance. Okay. For very, very large tanks, you level control, then a larger cycle time would be allowable. For very small or fast reacting system, you'll have to have almost instantaneous cycle time, a very high frequency, computation frequency. Right. PID control action. So now we get to the reverse acting and direct acting and forward acting actions of a PID. I just want to point out these definitions and descriptions which we are defining here. Many of these will be used to actually configure a PID block. There's a lot of variables to configure, 29 to be precise, to optimize and fine-tune your PID block. So you will need to know what each one of those variables are. However, many of these terms and descriptions you will not find in the PID block which you will configure, because those will be applicable to your plant, the actual actuator and the process and so on. So some of them will be used in our demonstration at the end, and some of them will not. So control action, the easy way to understand the control action, the forward the forward control action or the reverse control action, is to understand the effect the MV has to output on the process variable. So in other words, a direct acting or a forward acting PID controller is one where your output of your controller increases if your process variable increases. The reverse acting controller is one where your output or your MV decreases if your process variable increases. So if you look at a tank, for instance, we control the tank level, you get a drain valve, which can be a control valve, and you get a fill valve, which can be a control valve. Okay. So obviously your fill valve will have an opposite PID control action to your drain valve. Okay. Because if your process variable increases and you need to reduce the inputs of your tank, okay, then you will have to have a reverse acting controller. So that will be normally your fill valve, for instance, or a pump that has a filling of the tank. And then obviously vice versa, if you rather control the drain of the tank or a valve or a pump, then that would be a direct acting or a forward acting PID control action. Okay. So this is configurable in our PID blocks in GXWorks, as you will see a bit later on. Okay, then we look at the cycle period, which is different from the cycle time. So the cycle period is the period which the PID actually executes the calculation. So it's not necessarily dependent on your PLC scan rate, for instance. That would be your cycle time. This would be your PID performing a calculation. So you can let your PID calculate every second a new MV and send it to the controller, or you can do it every millisecond, depending on your application. Okay. So, however, the more powerful your CPU you have, or the more modern PLCs, you can have quite a high PID rate, okay, or a low cycle period. Because the higher the period, the lower your PLC performance. Okay. Let's look at the three algorithm factors very shortly. So as I mentioned earlier, this is only for introduction purposes, basic purposes. So we did omit all the complex mathematics from it, and we did replace it with descriptions so that you know what each one does. For part 2, obviously, we'll have a deep dive into a deeper dive into the mathematics. Okay, so the P factor. So this factor addresses the instantaneous error, the error which is your difference between your set point and process variable, and tries to mitigate it immediately, proportionally. So the bigger the error, the bigger the MV would react. The more intense the MV output will react to mitigate that error. Okay. So many understand the P factor as a current control. It looks at the current error, so that is correct. It doesn't look at the historical values. It doesn't look at future values, rate of change. It looks at the current values, so it reacts proportionally depending on the size of the error. Okay. The proportional factor will always be required, because you will always require your controller to react to the error. Okay. Then you get your integral factor. Okay, so the integral factor, like I said, it's a function of time. It looks at historical errors. Okay, so the error that's built up over time. And obviously, if this integrates or totalizes to a large value, your I gain, your I factor would be very large. It will react very intensely based on your I gain, which is user defined. Okay. And also, as I mentioned, if you see in your control system you've got a steady state error, then you just simply have to increase your I factor. Okay, so that's what we use for such errors. Right, then you get your D factor. So your D factor is your change of a process variable over time. So that's what's called a, I see I made a mistake there. It should be a derivative factor, not an integral factor. It should be a, this corner, yeah. It should be a rate of change measurement. So the faster your process variable changes, the higher your rate of change value, okay? And because it calculates the rate of change, you have now prediction. You can predict in 5 seconds, my error will be X, and therefore I need to mitigate it now. So it looks at historical values. I will just add as a side note, the D factor, as mentioned, is not the most popular one that's used. And when it's used, it's not very large. There are a couple of reasons for that. Sometimes your system, you don't want to overshoot. So you don't want the process variable to overshoot over your set point. Because if it overshoots, it would see the rate of change is too high, and then it would try to aggressively mitigate that. And then you get undershoot, overshoot, undershoot. And so that's why your D factor, if used in most cases for smaller systems, must be small. For larger systems, like large tanks and furnaces and so on, it's not very problematic. And also it's not very effective in those systems. So in many of those control systems, you will just have a PI controller. Okay. So if you see that your system has a lot of overshoot, undershoot, overshoot, so there's a lot of oscillation, then you just have to adjust your D factor. You just have to minimize that. In rare cases, or less common cases, you will have to change both your P and D factors to mitigate that. But first start with your D factor. Right, just a short summary of the structure of how a control system looks like. So you have your user, top here, in blue. So the user says, okay, fine, today I want to have this set point for my process. In this case, this process or the plant would be your tank level with your two variables, which is your control valve variable and your sensor. So your sensor will measure your tank level, and your control valve will be controlled by the PLC. Okay. So your sensor will sense the tank level. It would send that analog signal to the PLC as a process variable. Your PID would calculate the error and then adapt the output current or the output voltage going to your controller as an MV to address that error. And so the cycle continues automatically. Once again, that is irrelevant of the leaks and the size of the tank, and if there's any heat expansion, or if there's a difference in viscosity of the liquid. All of that is taken into account in your PID controller, because your PID controller wants to get a zero error as most effectively. So it doesn't look at other factors like the liquids and other properties. That is already included in your plant, all those elements. Another thing that needs to be taken into account, which we've seen, is where there are people who want to control their plant with a PID control, but they fail to do so because the errors keeps on increasing, irrespective of auto-tuning and so on. And we found in those cases that the output of your plant, like in this case a drain valve, if it's larger than your input, then control is impossible. Control cannot be done. Okay, so your output and your input must be either equal, or your input must be larger. Okay, so that's just an element to take into account. I just want to add another point here regarding the D factor. It's very sensitive to rates of change, because it's a rate of change. It looks at rates of change. Okay, and noise on your cable, your analog signals and analog wires, can be defined as a rate of change. Your PLC doesn't see that as noise. Your PLC see that as a very high instantaneous rate of change. So In such cases, you either have to totally um, shield your cables or move your cables away from anything that will cause noise. And if that's not possible, you're going to have to decrease your D-gain value. So it's not so sensitive to the noise. So D can be used as a damping factor for noise. Yeah. Just a couple of things here. So as I mentioned, your set points is usually defined as RT. This line here at the bottom, that will be your feedback. And your feedback will always be equal to your process variable. And in this case, your process variable is defined as YT. Okay. Then MV, in this case, will be UT. So MV would be your VFD's, your PLC's output. Okay, the analog output. So in this case, it's defined as UT. Okay. And then obviously the summation points would be where the algorithm is being applied. So this summation points where your PID algorithm is applied and generates the output. So just a simple description of how that works. Okay, so the principle of operation, your PID controller, the task of it is to force your process variable to match the set point. That's its objective. Okay, and your process variable is sampled as your feedback, FB. Okay, and those two are the same thing. Okay, so your PLC or your PID block in the PLC will have reached its objective if your error is 0. Your error will only be 0 if your set point, which is your feedback, equals your process variable. That's the only time you'll get an error. Otherwise, it will always constantly try to manipulate the output variable so that it can reach that 0. Right. So those are the two requirements as mentioned. So it either requires your error to be 0 or it requires your process variable in set point to be the same. Okay. Which means, and in fact, these two are exactly the same requirement because PV minus SP, it gives you 0, it means they are equal. Right. So your error will go to 0, will tend towards 0 as your set point, as your process variable tends towards your set point. Okay. So how does your error increase in plant in the first place? So your error increases if you, as the operating user or the plant owner, changes the set point. Immediately, an error is detected. Okay. Another factor that can increase the error is if there's a change in your process variable. So if there's a higher production, a higher drain, or a higher requirement in the plant. So more temperature is required or more flow rate, then that error will increase as well. So as mentioned, the output of the PID controller is UT, and in the PLC it would be parameterized as MV. Okay, and then the MV affects your process variable, which is your engineering value, if you look at it from a HMI/SCADA point of view. Okay, and that would be your process variable of the plant. And this will be the variable that's given back to the PLC as feedback. Of course, it's a closed loop system. From here, the error is being calculated and MV is being updated. And the system repeats itself iteratively and continuously. Okay. So all of these elements here, the process variable, the MV, and so on, they all are factors of time. So because the PID control system looks at time, current, present, and past. Okay, so if we look at the function block in JSWorks 3, so first of all, there are various types, various number of function blocks that is used in JSWorks 3, depending on the PLC you have. Like your modular PLCs will have slightly different PIDs than your compact PLCs. However, there are function blocks that's common to both. There are also older PID blocks, which you would find on your A series and your Q series, which is not used in your IQR series. So that also needs to be taken into account. So you get different kinds of PID blocks that's used. The most common one will be the one we have here, and that's the one that we will be using for this presentation, because this presentation is based on JXWorks 3 and FX5, the compact PLC. So you'll see that this block, everything on the left-hand side can be regarded as inputs, up and the right-hand side is regarded as outputs, and then it has 3 variables on the input side, if you exclude the EMs. So the S1, that would be your set point, or your target, your set value. Okay, so we know it's set point. S2 will be your process variable. That would be the one that's measured in the field. And then S3 would be your parameters. So all these elements which we discussed, or most of them, would be parameterized at S3. Okay, so take that into account. And then D would be your NB going to your plant. Okay. Note that many of my slides do have reference numbers at the bottom, which you can copy or use for your own research. Because, like I said, we're only covering the surface here. This is a long-term training course for such things. I think this is covered in our advanced PLC training course as well, to some extent. So, like I said, this is it's a long-term training topic. So we're only covering the surface here. But if you want to do your own research, or you have an applicable system in a plant and you want to see what the variable is, we have our pages here at the bottom. So you can have a look at the references. Right. So from a block diagram point of view, so you will have your input command. So that's to enable your PID block, which is equal to this EN here at the top. And then obviously you have your PV, SV, and your MV, and also your parameters, which is very important. So if you would do your fine tuning of your PLC, then the fine tuning would be the updating of your S3 values, your gains and your times. Okay. We have a deeper and specific look on that function block. Okay, so the parameterization coefficients that we use for the parameterizing of this block. Okay, so if you look at this S3 here, I can just go back. This S3 here, which is the same as this S3 here. That S3 consists of various consecutive. I have to point out the word consecutive, sequential words to configure this PLC. So it's not a one word. It starts at S3. So this first parameter that you will put here, your device, would be the first parameter or a series of parameters that needs to be configured for your PID. Okay. So these ones are the ones that's most typically used. There are many more. I think it goes up to 25 or 29, depending if you're doing auto tuning or just standard direct action or reverse action control. But these ones are the absolute minimum ones that you have to look at to have a basic control system. And as mentioned, we're looking at basic control systems here. If you want to have a more in-depth control system and you want to look at more variables, then the page number here, bottom left, you can have a look at that. Like I said, there's eManual Viewer. It's freely downloadable from some of our knowledge base sites, also from the main Mitsubishi site. You will find the latest version there. And if you can't find it, you can just drop me a mail. I can give you a link to that. So it's very valuable, and there's a lot of detail in there. Okay, so let's have a closer look at these parameters here. So S3 would be your first word, your D word, your first address. So that's your sampling time. So as I mentioned, your sampling time, that's directly proportional to your PID cycle time. Okay, so that would affect your update time of your PID's process variable. Okay, so the sampling time is how fast it would take the samples. In this case, the sample would be your PD, your plant, your process variable. Okay. Then also, as you would recall, we discussed the direct action or reverse action. So many would say it's 50-50. No, it's not. I will say direct action is by far the most common, but there are still many reverse action applications. So yeah, that's highly dependent on your process. So you need to change that accordingly. Another thing to take into account is if you want to alert the rate of change of the inputs and also to get an alert alarm for the rate of change of the outputs. We're not going to use that in our example. That's an additional nice to have add-on. But that can be used for interlocking. It can be used for alarming. It can be used for display. And whatever you want to use your control system variables for. Okay, bit 3 you would ignore completely, and bit 4, that's what you would use to either have a direct action, reverse action control, or auto tuning. Okay, so we're not going to do auto tuning, so that would be a 0. And bit 5, you would enable that bit if you want to limit your PLC's output. Okay, your MV output range. Okay, some vendors would call it your resolution output. Okay, and that would be in most cases be dependent on your analog output resolution, your bit resolution. Okay, so some PLC outputs have got a 0 to 4000 resolution, 4095 to be precise. If you use the full range, but standard 0 to 4000. Some has got a 0 to 8000. I've seen some with 32,000 or 16,000. So you can change that. The upper limit by default is 32,000. Okay, so 32,000. So we will have limit that to 32,000, and we will keep the lower limit to 0. And then your bit 6 would be your what type of control system you have, step response, limit cycle method. We'll just keep that as 0 as well. Bits 7 to 5 on this word, so this is a single word, it's not used. And for your input filter, your second variable, you've got your input filter constant. So that is like a noise filter. So if you have a lot of noise in your wires, you can add a filter constant. Okay. If you're unsure, you can put a 50% or 70% and see if it works out. And you can change that. That's also changed by auto tuning. Then you've got your gains. You've got your proportional gain KP. You've got your integral time, which is a factor which you multiply by 100 milliseconds, your derivative time, and your derivative gain. Okay, so this will be used on these words here. Okay, right. Just more detail on your filter constant. So that would be for your noise. That's measured in your PV. And if you have if your plant demands that you have a D factor, then you will have to implement a high filter constant. Okay, more information on this page. Right. Those variables which we discussed, the ones that are marked in yellow, these ones would be traditionally normally used as minimum requirements for setting up your PID control system. Okay. So just something to take into account there. This is the number of the page if you need more reference on that. Right. So this is an example of how to configure a PID block. So as I said, your S3 would be consecutive values. So you can use a D register, which is a word, and then you can have consecutive 29 registers defined for your S3. I say 29, but we only use a couple of them. 29 if you is allocated and preserved for this PID consecutive blocks. And then obviously you have your elements such as your process variable, set point, and your manipulated value, all as D values. Okay. Right. So just as a demonstration on how this would work, I have this here. Right. So here we've got a little block which we configured already. So the sampling time, I made 200 milliseconds. Can make it much faster. Then your operation settings. Okay, so if you recall from the presentation, it would be these bits here. Now, these bits here are consecutive bits, and if you have a consecutive binary word bits, it's expressed as a hex value. Okay, so if we just let me see if I can start my calculator here. Okay, so I'm just going to put it to programmer calculator so we can have some conversion here. So I want to turn on bit 1, for instance, for backwards control. So then I have a 1, want to have all of them 0, so it'll be 0, 0, 0, 0. Okay, so it'll be 0, 0, 0, 0. Sorry, it must be binary. Yeah, so it would be 1, 0, 0, 0. Just do that again. So just change that. So it'd be 1, 0, 0, 0. Another 0 and 1 there. Okay, because that one is 1. This one's 1. So then we have a hex number of 21. So this will be the number that we'll write to the block. For this number here. And that's what we got there. H21 there. For P gain, I chose 200 milliseconds. I gain 100 milliseconds. D gain 10 milliseconds because I want to emit noise. And your T time 10. And then my output of this PV, I made it 0. I don't want it to be go low to 0 because it can go up to minus 32,000. And my upper limit, I made 32,000. But this can be 4,000 or 8,000, depending on your analog card. So if we do a simulation here, okay, so the program is running here, and I use SCM here, which is your always on bit for your PLC. So the moment your PLC starts up, it will move all of these coefficients into your parameters, which is all linked to your S3. So now if we enable our PID block, okay, the output stays 0. Why is the output staying 0? The output stays 0 because your error is 0. Your error is 0 because your set point and your process variable is the same. If we go now and we change my set point, I want it to be 1,000, or let's say 50% for the tank level. 50. Okay. Now we see that the PID is now sending an analog signal to your valve or pump, and it is trying to mitigate that error. And as you go closer to that error, let's say we are 36% now, you will see that this value is updating slightly lower. And if you go very close, it would be very slow changing because now it's reaching that steady state error, okay, to reach that set point, okay. And then if we reach 50, your PID stabilizes. However, if we go overshoot, if the tank goes too high, for instance, or temperature goes too high, now you see your output lowers. So now your PLC tries to reduce that error. And obviously, the bigger the error, the faster it will try to reduce that error. Okay, so that is how that will work. I'm going to, if you can send me your email address, I'll send you this presentation as well as the PLC sample code for your own use, and also a link to the eManual viewer, just for those who are interested. Right. Right. Just a couple of abbreviations and acronyms that's used in this presentation. So we will discuss all of these in detail. Also, these ones has been discussed in this presentation. Okay. These are the resources for reference if you want to read more on the content of this presentation. Okay, and now we can, if there's any questions, you can let me know. We'll just keep a few minutes for questions, if any. I know there's an outstanding question for a previous webinar regarding the pointers that's being used in the structured text. We are working on that, and we will send you feedback on that. Seems like we have got no questions thus far. Okay, so like I said, many of you would know most of these elements. So many of you want to have more information on this, you can drop me a mail and I'll give you more information. For those who are aware of most of these elements, please be in touch and keep an eye on our marketing website for the part 2 of PID control and part 3. Where we're going to have a more technical deep dive on how to configure and auto-tune these PIDs. And also, very importantly, how to interface this to other devices like your GOTs, SCADAs, Android SCADA, and your VFDs and so on. Okay, guys. See, there are no questions here, so then we will call this a day. Perfect.